Welcome to This Explainer. I'm absolutely thrilled you're here today because we are going to completely demystify kinematics. But look, we aren't just going to stare at boring flat lines on a page, okay? We're taking the rigorous, high-level concepts of AP Physics and combining them with the kind of gorgeous Pixar-style animation lighting you'd see in a summer blockbuster. Add in some incredibly focused AI-generated music, and boom, we're creating a cinematic classroom right here, right now, to make sure these concepts stick in your brain for good. So get ready, because you're about to see physics in a whole new light.
It's a question that plagues physics classrooms literally everywhere. Why do most students just memorize motion graphs without actually understanding them? You've probably been there yourself. You stare at a line moving up and to the right, you memorize some formula, and you just kind of hope it's enough to pass the test. But that traditional memorization, it completely fails because it lacks visual depth. It completely disconnects the math from the real, moving world. Well, in the next few minutes, I promise you this explainer is going to change how you see motion forever. We're taking the abstract and we're making it real.
Okay, let's dive into this. Here's our agenda for today. First up, mastering velocity versus time. Second, cinematic lighting for depth. Third, setting the educational mood. Fourth, interpreting slopes and areas. Fifth, avoiding common kinematics mistakes. And finally, number 6, our summary and final thoughts.
Section 1. Mastering velocity versus time, the foundation of motion.
Okay, if there is one single vocabulary word you absolutely must lock into your brain when looking at these specific graphs, it is this: acceleration. Acceleration is simply the rate of change of velocity with respect to time. Mathematically, you'll see that written as A equals delta V over delta t. In plain English, it just means how fast your speed or your direction is changing. So whenever you look at a velocity time graph, your brain should immediately start hunting for the acceleration.
Let's break down the physical layout of the graph so you know exactly where everything lives. On the horizontal x-axis, we map out time. On the vertical y-axis, we plot the velocity. Now here's where the absolute magic happens. The slope, the steepness of the line, that tells us the acceleration. A positive slope means positive acceleration, and a negative slope means deceleration. But the absolute coolest part? The physical space, like the actual area trapped under that curve and above the time axis, represents the object's total displacement. It's literally like a hidden map of distance inside the graph.
Moving right along to Section 2, Cinematic Lighting for Depth, Visualizing the Physics.
So think about those Pixar-quality educational animations. Lighting in those scenes isn't just about making sure you can see a car on the screen. According to animation experts, lighting serves 3 core purposes. It supports the storytelling, it brings out 3-dimensionality, and it creates mood and atmosphere. By applying these high-end, cinematic lighting techniques to a digital sports car in our minds, we stop seeing a flat, boring dot on a grid. Instead, we start seeing a heavy, textured machine actively tearing down a road.
Lighting defines depth, volume, and texture. When we illuminate a 3D model of a moving car with really realistic lighting and smooth camera movements, your eye naturally connects the abstract mathematical graph to realistic real-world motion. So when the car accelerates, when that graph's line shoots upward, you aren't just seeing a line anymore. You actually visualize the dynamic weight of the car shifting backward, highlighted by the sun bouncing right off its metallic paint. That incredible visual depth is exactly what makes the physics utterly unforgettable.
Section 3. Setting the educational mood. The power of AI audio.
You might not even realize it, but the background audio playing during a lesson drastically impacts how much information you retain. Tools like 11 Labs can now generate these incredible royalty-free tracks specifically engineered for education. Take a look at these examples. A track like Digital Sunrise uses layered synth pads and marimbas and this corporate pop style to evoke a really highly productive, uplifting mood. Or take Positive Strides, which uses acoustic guitars at a nice moderate tempo to keep you motivated but completely calm.
The crucial takeaway here is that sound design is a totally deliberate choice intended to support focused and engaging learning environments. When you're just about to jump into hard numbers and calculate slopes, a moderate, layered instrumental track strips away all those outside distractions and primes your brain for serious analytical thinking. So we've set the visual stage, we've set the audio mood, let's get into the math.
Now, what's really interesting about this next slide is how we actually apply this. Section 4, Interpreting Slopes and Areas. Let's do the math.
All right, let's walk step by step through a concrete AP Physics level example to find displacement. Remember, displacement is the area under the curve. Imagine our cinematically lit sports car. Step 1. It starts from rest.
so its initial velocity is exactly 0. Step 2. It accelerates uniformly to 20 meters per second over a total of 4 seconds. Step 3. If you draw this out on our graph, a straight line going from 0 to 20 over 4 seconds forms a perfect right triangle right underneath it. Step 4. To find the displacement, we just calculate the area of that triangle. The formula is 1/2 times base times height. So that's 1/2 times our base of 4 seconds times our height of 20 meters per second.
Boom! 40 meters. The physical space that you shaded under that velocity curve literally translates to the real-world distance that car just traveled down the highway. Once you start seeing the area as a physical distance, I guarantee you will never look at a graph the same way again.
Okay, let's try one more, but this time for deceleration. Imagine the car suddenly hits the brakes. Step 1, our object is moving at a steady 15 meters per second. Step 2, it decelerates to a complete stop, rest, over exactly 3 seconds. Step 3, on our graph, this creates a straight line plunging downward from 15 down to 0. It's a negative slope. Step 4, to find the acceleration, we calculate the slope. That's the change in velocity over the change in time. Our final velocity is 0 minus our initial velocity of 15, all divided by the 3 seconds it took.
Which gives us a super clean result of -5 meters per second squared. And guys, that negative sign right there, it is absolutely crucial. It isn't just a math quirk, it is the actual physical indicator of direction. It's telling us that the acceleration is acting opposite to the velocity, effectively slowing the car down to a complete halt.
And this brilliantly illustrates one of the biggest points of confusion I see for students, comparing the velocity time graph directly to the position time graph. Look at this. On a velocity versus time graph, the slope is acceleration, and the area is displacement. But on a position versus time graph, the slope is velocity, and the area under the curve? It's completely meaningless. It's not directly applicable at all. You absolutely have to know which graph you are looking at before you start punching numbers into your calculator.
Section 5. Avoiding common kinematics mistakes, the pitfalls.
Here is the number one absolute most frequent error out there. A student looks at a steep, rising slope on a velocity time graph and immediately thinks, wow, that object has a super high velocity. No, that is a trap. The correct interpretation is that the slope equals acceleration. A really steep slope just means the velocity is changing really fast. The object itself could actually be moving incredibly slowly, but simply accelerating really hard. Please do not mix those up.
And here are just a few other major pitfalls to dodge. First, forgetting that the area signifies displacement. Guys, it's literally free information sitting right there on the graph. Second, misapplying sign conventions. Remember our braking car from earlier? If you drop the negative sign, you are telling the examiner the car is speeding up, not slowing down. And finally, ignoring units. This is a classic total disaster. If the graph gives you time in minutes and velocity in kilometers per hour, you absolutely cannot just multiply them without converting first. Always check your units to avoid a total calculation meltdown.
Section 6. Summary and Final Thoughts. Visualizing Motion.
Let's quickly review our key takeaways. The velocity time graph is your ultimate tool for visually representing changes in velocity. The slope of that line always indicates the acceleration. The physical area underneath that line, that gives you the total displacement. And fundamentally, we've learned a really cool meta lesson today too. Using cinematic lighting to visualize 3D volume and layered AI music to set the mood drastically elevates our focus and our ability to actually grasp these tough mathematical concepts.
Before we go, I want to share this fantastic examiner tip sourced from Sparkle. If you ever just completely blank out during a test, use the mnemonic SLOPE. It stands for sum of lines overall pattern equals acceleration. It is a quirky but highly effective little memory trick to make sure that core concept sticks with you right into the exam room.
So I'm going to leave you with this final provocative thought. The next time you are out in the real world, maybe you're watching a movie with a brilliantly lit cinematic car chase, or you're just watching a car pull away from a stoplight, don't just blindly look at it. I challenge you to mentally graph its velocity. Actually see the slope of its acceleration in your mind's eye and visualize the area of displacement stretching out on the road behind it. Because once you can do that, you haven't just memorized physics, you have truly mastered it. Thanks so much for joining me in this explainer, and keep observing the motion all around you.